Hello, everyone, and welcome to the Weekly Space Hangout for Friday, November 4th, 2016. I'm Fraser, Cain, publisher of Universe Today. This week, we got a bunch of stories. We're going to be talking about the mass of the dark matter particle, if it exists.
Hey.
The James Webb Space Telescope Sunshield is done. First light on the Very Large Telescope's new adaptive optics, and the entire sky mapped in hydrogen, which is a really cool picture, which I hope I can get posted up as well. So, joining us this week, we've got a bunch of our regular cast of characters. We've got, let's see, Paul Matt-Sutter.
Yes, you do.
Yes, we do. All the Paul Matt-Sutter. We've got
which is just one.
Just
but that's
one.
all you need.
Someone says that you were given a plant for your prison cell.
Yes, I would say, and it's not even a real plant.
It's not even a real plant?
No, it's totally fake.
Oh, no.
But it looks nice. It's a nice looking plant.
Yeah.
There it is. Look at that.
Oh, that's awesome.
I see that.
We've got Kimberly Cartier. Kimberly, welcome.
Hello, everyone.
There she
I'm
is.
here. I don't have a plant.
You nowhere? No.
You don't have a prison
I
cell.
don't have a plant.
You know what? Don't get plants. They fall in your backyard. You can't trust them. So, I don't recommend.
They're always out to get us.
Yeah, exactly. And so let's. So first, before we get into our, actually, you know what? I'm going to introduce our special guest first. We've got Dr. Matt Golombek from NASA.
Hi, everybody.
Awesome! This is so great. I'm so excited. So for anyone who is just joining us for the first time, of course, this is a live, interactive show. You can talk to us, and we can talk to you. If you're watching this live, if you're watching this after the fact, I'm sorry. You'll need a time machine. But the way you can do this, of course, is wherever you're watching the live show, we've got a live chat over on YouTube, and then we also have this chat down here, which is the WSH Cruise Slack channel, and you can go ahead and join that and participate in that conversation. And there'll be instructions every now and then posted in right there. Just happened on how to actually join the conversation. So if you want to join the community, this is the way to do it. And a big thanks to the Weekly Space Hangout crew for organizing this week's guest, which is just awesome. So, all right, let's move on to our guest this week. And man, this is so exciting. So, Matt, welcome to the Weekly Space Hangout. And why don't you give people just a quick explanation of who you are and what you do?
Hi, everybody. So I'm a planetary geologist, and what I do for a living is select landing sites on Mars. I help operate rovers on Mars, and I instruct the orbiters to take pictures of places that we're thinking of landing to evaluate their characteristics to make sure that they're safe and scientifically interesting.
So let's start with the selecting of landing sites on Mars. So which of the landing sites were you involved in, and what is sort of the general process to find a good spot for a rover lander future colony to go?
Well, future colony, that's different from the ones we've sent so far. Let's see, I've been involved in all of the landing site selections in the recent era, so from Mars Pathfinder to now, that's 5. And generally there are 2 sorts of constraints that go into site selection. One is the engineering constraints. This is a spacecraft that comes to land on the surface in a very specific way, and each one is engineered slightly differently. And you must understand exactly what will make it safe and what won't make it safe. And you must decide which those parameters are important, and then you have to measure them on Mars to make sure that the place you are going to go is safe. And the other half is, are the materials and rocks and things that you want to measure on Mars available at that site to allow you to address the science objectives of that mission? And of course, each mission is different in that regard too. So each site selection is an interesting pathway and that we all must take together.
So I guess the issue, of course, is that you're trying to really balance the science that you're going to be accomplishing as well as the safety concerns about the spacecraft itself. And as we've seen, Mars eats spacecraft for breakfast. So how does that balancing act work out?
So partially it depends on the size of the landing ellipse, but first of all, safety has to be job number one, because it doesn't matter what your hopes for science are if you don't land safely. That's the difference between a rover and a lander and an orbiter. So if you're not going to land safely, you shouldn't be going there in the first place. And so generally, safety is always the first thing we look at. But we always look at it at the same time that we're looking at what science that spacecraft needs to do. Because if you send a rover to an incredibly boring flat plane where there's nothing interesting to look at, that's not a very good choice either.
Yeah. I think, right now, or up until this point, a lot of the rovers really have they've erred on the side of caution in some cases, but I can see that sort of as the missions are getting more and more, as some of the basic science is getting done, it seems to be the sort of willing to push the danger zone a little more to try and get at some of the more interesting targets, right?
Yeah, and it depends. So I think one of the biggest changes is that our landing ellipse early on was 150 to even 200 kilometers across. So you need something that's smooth and flat with no rocks and no scarps and steep hills, etc. And that tends to push you to places that are smooth, flat, and boring. On the other hand, our technology now has gotten the landing ellipses down to 10 to 15 kilometers. And what we're looking at for the Mars 2020 mission is the ability to map hazards and avoid them on your final descent. So you can actually find a location that might have lots of truly interesting scarps that you would love to explore scientifically, but yet you can avoid them on the final landing. And that has made the selection much, much more, I wouldn't say daring, but really going to the places where you can address key scientific topics. And thus much more interesting in that regard.
Now, a lot of people watching the show are very familiar with space, so they know about the Mars exploration rovers and the work that they've done, familiar with Curiosity. So for the missions that are coming up, there's the InSight lander, there is the upcoming 2020 rover, what the Europeans are doing with their ExoMars. What parts of Mars will sort of fall under future exploration?
So in general, spacecraft like to land near the equator of Mars because the thermal constraints on the day-night cycle are much more predictable. And if it's a solar-powered vehicle, it gets much more insulation near the equator than elsewhere. So you tend to look at the equator first. The second most important thing is you need a lot of atmosphere. Mars's atmosphere is dramatically thinner than the Earth's, and all of the spacecraft that we've landed so far use parachutes and retropropulsion. And so if you have more atmosphere, you have more time, and you can slow yourself down better if you have a lower elevation site than a higher elevation site. So those are the two big things that sort of right off the bat. Once you get for beyond that, for InSight, which is one extreme, if you will, there are very few science constraints. What it's going to do is put a seismometer on the ground, and you can measure Mars quakes almost anywhere. And it's going to put a heat flow probe that's going to thump its way down into the ground to get at what the temperature of the planet is. So you're looking for a place that isn't so science friendly as much as can you get a heat flow probe down 5 meters, and is it smooth and flat over a big ellipse? Versus the Mars 2020, that's a rover kind of like MSL or Curiosity, but now that's going to collect samples and cache them for eventual return to Earth. So think of those samples as the ultimate silver bullets in space exploration. These are the dearest things you could possibly collect from Mars. And you want to get the most important samples that would tell you about the early environment on Mars and whether or not it was habitable. And even more fundamentally could life have actually started on Mars at a time when life got going here on the Earth? So those are incredibly different directions to go, and that's what makes site selection fun.
And what would be a location that maybe is perhaps too dangerous, is interesting, but maybe a little too risky? I mean, you said that, sticking to the equator so you can get that sort of thicker atmosphere, and I guess, more sunlight to keep the rover's solar panels filled, unless it's, nuclear powered or, has a nuclear RTG. But, what are some places on Mars that you would love to see explored in the future that are just, everyone just keeps going, too dangerous?
Yeah, and actually we're targeting many of those, or studying many of those areas now for the Mars 2020 rover. And they tend to be locations where you have a wide diversity of rocks, and you have clear evidence from the mineralogy of those rocks that it could have been an environment that liquid water was stable and contributed to the deposition of those rocks. Think of layered sedimentary sequences with clay minerals, for example, in which organics could be sequestered and kept intact for long periods of time, such that your rover could go to them and sample them and put them in a test tube for eventual return to Earth.
Yeah, that is the absolute holy grail, is to be able to bring some of that material back from Mars and be able to test it out. We've got a couple of questions coming from the viewers here, and I want to run some of these questions past you because I think they're pretty great. So there's a bunch of people asking about SpaceX and about their plans with the Red Dragon, and have they come to you at all, and are they looking for any assistance in suggesting some sites for the Red Dragon to go to in the first place? And maybe, do you have some recommendations about where a colony could go?
So their initial suggestion is to, in fact, land something in, 2018 or maybe 2020. Well, that's pretty soon, and they have come. There is an agreement between SpaceX and JPL or NASA, and we are helping them with characterization of the surface and actually beginning to look at places they might be interested in landing. Because of the way they land, which is quite different from the way NASA has landed spacecraft up to now, they really need to go to a very low elevation. They need a lot of atmosphere to slow themselves down. So they're looking at things with elevations below -4 kilometers above the datum on Mars. Really way, way down, lots of atmosphere. And we're looking at suggestions for whether that first mission might be a place that just proves that their spacecraft can land on Mars versus their long-term goal of actually finding a place where they could set up a colony and actually have people living there. And the big difference there is the latter would require resources, and the most important one on Mars is, of course, water. And so you probably need to go to higher latitudes to find that water on Mars versus the equator, which might be easier but doesn't have that water.
Right, and this is, of course, the problem. I guess, there's that thicker atmosphere issue, and I'd be interested to know just how much of an advantage you can get. Like if you land in, say, the bottom of the Valles Marineris, how much more atmosphere are you able to use to slow down your spacecraft than, say, if you landed just on the plains?
Yeah, so I mean, think about how much atmosphere there is at the top of Mount Everest and why people carry oxygen tanks up there versus the amount of oxygen in the bottom of Death Valley. And it's exponentially more dense as you go down. And so the lower you are, you have a dramatic increase in atmospheric density, which you can use to your advantage during landing. So that's really kind of required. For SpaceX, they have this is the big capsule, the Dragon capsule. That's a big spacecraft.
Yeah.
They need a lot of atmosphere to slow themselves down.
Yeah. I mean, this is still one of the great challenges, and we've had a great series on Universe Today. Nancy Atkinson wrote this great series just about how hard it is to land these large payloads on Mars because the atmosphere is just the exact wrong level of thickness.
Yeah, exactly.
For both, for both trying to use it for aerobraking or for attempting to.
Yeah, if it was way thicker, you'd always use a parachute. If it was way thinner, you never would. And Mars's atmosphere just kind of in between, and you kind of wind up using both, or it's tougher, way tougher.
Yeah, absolutely. But then I guess from a colonization standpoint, you want access to water. You want as much sunlight power near the.
Yeah, that's right. So the higher in latitude, you got this yin and the yang, so the higher in latitude you go, the insulation decreases in the winter, of course. It's also energetically tougher to get off of the planet because you're farther from the equator, and Mars is a spinner, and you can use that to help you launch from the surface. So you're going higher in latitude, that's where the ice is, but you're getting less energy and you've got worse energetics. So everything, there's an adage in landing site selection, there's no such thing as a perfect landing site. There's always trades.
I believe it's the ones you can walk away from.
Those trades to find the right one.
Yeah. I got a couple more questions here coming in from the viewers. This question comes from Truck Captain Stumpy. Can you tell us about this latest iron meteorite find on Mars? And we report on this quite a bit. There's a metal meteorite on Mars.
Yeah, so I think Curiosity just found one. This is not one of the larger ones. They have found bigger ones in the past. And iron meteorites are pretty interesting on Mars. Not because they're there. We think there ought to be a lot of them. They come from the asteroid belt. The interesting aspect about an iron meteorite is it was the former core of a planet that was out at the asteroid, and it's been perturbed and landed on Mars. What's really extremely interesting for us for finding iron meteorites on Mars is two things. One is, how do you get them down to the surface and have them survive the trip? If they're coming in at hypervelocity impact speeds, they form craters and there's nothing left of the impactor. It basically vaporizes. But when you look at these meteorites that have a clear form, they have what we call regmaglyphs, which are these ablation portions of the meteorite. That's a sample of that meteorite interacting with the atmosphere as it comes through the atmosphere. So that means that meteorite's been slowed down enough that it could survive landing on the surface. And it's not going kilometers per second. It's going much, much more slowly. And thus, then, you can use that meteorite for two things. One, to determine how thick the atmosphere needed to be to slow it down and what its pathway through the atmosphere was. Oh. And secondly, almost as important, is if you put a piece of iron meteorite in any oxidizing environment, it rusts out in no time at all. And the time it takes for an iron meteorite to rust out on the Earth is, it's very, very short. They don't last. So they're kind of these witness samples of this pure material that will change form extraordinarily rapidly in contact with liquid water. And thus, it tells you how long it's been dry and desiccating on Mars.
And could possibly tell you if maybe the atmosphere was thicker in the past, if it had to pass
that's
through
right.
Mars.
So if you look at, in fact, the largest meteorites that Curiosity has found, they're so big that you need to have made the atmosphere thicker to have slowed them down and landed them on the surface in the past.
That's super interesting. I mean, it tells you what kinds of activity is going on the surface, how quickly it can be rusting away. Because, we see all that. Everything on Mars is this oxidized material. So there is this oxidizing activity going on. But now we actually get to see something where you can try and get a sample, I guess, a sense of when this happened, and then literally just watch it. That's amazing.
And how fast that oxidation has occurred with respect to what the environment. So it tells you about the environment, in fact, since the meteorite's been sitting there on the surface.
And the chances of finding this was pretty low. Like, this is just an amazing find then.
So we actually think that just like on Earth, there's lots of these meteorites falling all the time because the atmosphere of Mars is much thinner than the Earth's. It's actually easier to get more of these things down onto the surface without burning them up in the atmosphere. And we expect you'd find a whole slew of them. And we actually have found quite a large number on the surface. So maybe the fact that we found them is less surprising than how pristine many of them are and what that says about the environment since they were landed, if you will.
Oh, just absolutely awesome! I was as soon as I saw the picture, I'm a huge fan of metal meteorites, and I've got a collection of my own. And so the fact that one of these has been found, I mean, I saw the picture, and I'm like, that's just like what I've got, except it's different, right? Except that it went through a different amount of atmosphere, got heated in different ways. So it's absolutely.
And you'd say, why would somebody who finds landing sites on Mars be all that interested in meteorites? And I'll tell you why. Because the way you land a large iron meteorite on Mars is the same way we land spacecraft. We target almost the skip out point on the edge of the atmosphere to enter the atmosphere and use as much of that atmosphere as possible with a spacecraft to use that atmosphere to slow you down. And that's how you land. If you come in directly perpendicular to the surface, you're going to burn up and or hit and you'll never survive. So you target the very margin. And if you're too far, if you miss it, you skip out and but you just auger it enough that you take these really long pathways through the atmosphere to slow the spacecraft down on the air shell. So we target that with our spacecraft. And those are the meteorites that will survive the atmosphere on Mars. They're coming in just glancing, and they use these really long pathways. So somebody who lands spacecraft on Mars is really interested in these iron meteorites.
Right. Something made of metal made it to the surface,
right.
Didn't explode, didn't skip off into deep space. Perhaps it's possible. Which is great. So I got sort of one last sort of line of questions here, and this is sort of based on a question that came from Arjun, which is that what areas of Mars would be good sites for human astronauts to test for past life? But I mean, it's not just human astronauts. What are some areas on Mars that would be great places to test for past life? I mean, this is sort of the next great phase in NASA's exploration of Mars. So
yeah, so now think about, so I told you about the two important factors that go into site selection for any robotic mission. It's safety and it's science interest. But now with a human mission, and imagine a colony, now resources become almost as important. And you need large quantities of water to support humans on the surface, and to create the fuel, the oxygen and the hydrogen that we would use for getting there. And I mean, you don't want a one-way trip. You want to be able to go there and come back. So now you need large quantities of water, and you need to find a place that now it's safe. It has all of these resources in a manner that you can collect them at the surface, and it has key deposits that you could investigate past life. So think of it. It's a troika, if you will, and you need the perfect combination of all three. And we don't even know if such places exist.
Right.
That would be a very, very interesting aspect of trying to find them, for sure.
Yeah.
And again, you'd be pushed, just as the Red Dragon exercises showed, you'd be pushed to the higher latitudes, to 30 to 45 degrees north latitudes, where we do see ice in the subsurface. So those would be the resources. And then places where sedimentary rocks were deposited by flowing water with minerals that suggested the interaction of that water with the rock. And then nice smooth places to touch down and that you could drive between the habitat and the place where you put your power source, and big flat areas for putting out your solar panels and so on.
Oh, that's fantastic. So as people are sort of keeping track of things, what is the next major event? I know that the European ExoMars just arrived. We lost the Schiaparelli, but the orbiter is there. what is the next big event in NASA's exploration of Mars? What's happening next?
So in 2018, the InSight lander will touch down in Elysium Planitia. We just finished the site selection for that, and that will place a seismometer and heat flow probe. This has been an aspect of Mars exploration that's really been neglected. We've been looking at the outside and the interaction of water with the surface, but that's closely coupled to what's been happening to the interior. How active is the convection in the mantle? Is there exchange between the rocks and the atmosphere in the interior? And the activity level is very important in that regard. So InSight will create a much stronger view of the entire planet and the interior. I mean, after all, 99% of the planet is inside. And this will give us an idea of how active it is and how much heat is getting out and how that heat is getting out. And then that tells you where the water is and where the water is going. So that's really a key. In 2020, either the ExoMars rover may go in 18 or 2020. It's not determined yet. But in addition, the 2020 rover would go, and that would be caching and collecting samples for eventual return to Earth. The ExoMars rover can roll around and drive around, but also go down several meters to look beneath that surface oxidizing layer. That's very exciting. And then there are studies for what things we would do after that. And those sort of studies are suggesting an additional orbiter to continue the capability that the Mars Reconnaissance Orbiter is doing now, the ability to survey the surface, take high resolution images so that we could continue to find landing sites for future surface exploration. And then maybe Red Dragon comes into the picture and the private sector starts placing payloads on the surface. It all adds up to a very exciting exploration program for Mars.
Yeah, Mars is going to be a pretty busy place for the next couple of years. That's
Yeah,
exciting.
yeah.
So where do people find out more about what you're working on? How can they follow you on various social media and stay in tune?
So, I mean, certainly NASA has great websites that describe all of the NASA missions. We are the civilian space agency. Everything we do is in the open literature. There's no secrets here. And of course, you guys can find out about what we do all the time. Our workshops for finding landing sites are open workshops, open to basically anybody who's interested can come and participate. So that's all open and available to anybody. Yeah.
Fantastic. Well, Matt Golombek, thank you so much for joining us again on the Weekly Space Hangout. It's great to have you back. And maybe when InSight is on its way or lands, we'll get you back for another conversation about that.
Happy to speak with you again.
All right. Thanks for joining us.
Bye-bye. Yeah.
All right, let's move on. Kimberly Cartier, I want to talk about the entire sky mapped in hydrogen.
Oh, now this is one of those things that is also incredibly cool, but not just amazing to look at, but incredibly powerful scientifically.
And it's a really cool picture. I'm going to bring up the picture here.
Oh, cool.
Yeah.
It looks so fantastic. So a collaboration of astronomers from around the world spent, from 2005 to 2013 mapping the entirety of the night sky using radio telescopes based at the Parkes Observatory in Australia and the Effelsberg Observatory in Germany. And they were looking for neutral hydrogen, which is which is the most abundant element in the galaxy and the universe. And they're looking for radio emission from neutral hydrogen, which can be detected in radio waves at about 21 centimeters. And they spent almost a decade collecting observations and then many, many years analyzing all of these data to create the highest resolution and the most temperature and radio velocity sensitive full sky map of hydrogen in our galaxy. And when you can do that, you see every little speck of hydrogen that's capable of creating stars and planets, and you get to see some of the most fine detailed structure in our galaxy. And if you're looking at the image or the videos that they have, you can very clearly see things like the disk of the Milky Way. You can see the center of the galaxy. You can see the large and small Magellanic Clouds.
I was wondering, is that them
Crazy.
down on the bottom
Yeah,
right of the image?
Yeah, if you're looking at that full image and you see those two splotches in the bottom right, those are the large and small Magellanic Clouds. And there are a few smaller star-forming regions towards the bottom left as well. And everything, that big stripe across the center, that's the disk of the Milky Way. That's where the majority of all action is happening in our galaxy. But you see that the galaxy is not just contained to this tiny disk with a few orbiting dwarf galaxies. You see the swirls of hydrogen that go all the way around the sky that extend way beyond just the spiral arms. And it's just incredible to see, I have to say. It's very stunning. They have resolution, like incredible resolution down to like 40 millikelvins in temperature for the gas. They have precise hydrogen abundances everywhere. They can tell whether the gas is moving towards us or away from us, so they're getting kinematic information. It's just incredible amount of data. And it's all publicly available too.
Yeah, and now it's an absolutely beautiful picture, of course, but what is the scientific purpose of this? So...
Right. So the scientific purpose of this is, it sort of encompasses all aspects of astronomy. If you're interested in the galaxy, we want to know how old the galaxy is, where the galaxy is capable of forming stars, how things in the galaxy are moving around. So you get information about the gravity. You see where stars are capable of forming, how old these things are. So we're actually, with this map, we were able to detect very tiny pockets of gas that are still capable of forming stars, and probably where most of the stars in the galaxies formed, in these very tiny gas clouds that we would not otherwise be able to detect. And we're seeing that everywhere. And if you want to look at distant galaxies out in the cosmos, you still have to look through all of this hydrogen. You need to know where it is and how to take it out of your images or your spectra in order to understand what that distant galaxy or quasar or active galactic nucleus is actually doing. Sort of like how...
I was going to add to what that your excellent summary, but if you have more to say, you can say.
I was going to say this sort of encompassing cloud of hydrogen almost acts like the Earth's atmosphere, and that any observations we take from the ground, we have to look through the atmosphere. Any observations we take of distant galaxies, we have to pass through all this hydrogen.
So Kimberly made an excellent point that when you're looking at neutral hydrogen, this encompasses so many areas of astronomy and astrophysics and even cosmology. That was a very good analogy of having to look through our atmosphere. When you see that map, this beautiful image that it produced, some of that light, 1 part in 10,000, actually originated over 13.5 billion years ago before stars even formed. This is a cosmological era that we call the Dark Ages, where the universe was almost entirely neutral, just made up of neutral hydrogen, but was glowing, emitting at 21 centimeters. And it has propagated all the way to today. If we want to study that epoch, which we have not had any images of that epoch ever yet, if we want to study that, we have to understand what these foreground structures are, the stuff in our own galaxy, the stuff in our own neighborhood is, so that we can kind of look behind it and dig out the cosmological information. So when I see that map, I just see a bunch of junk that I want to get rid of. Others find value in.
Gotcha.
But one person's trash is another person's treasure.
Yeah.
Yes. When my group was over at the Green Bank Telescope last week doing radio observations, we actually already utilized some of these data when we were looking at Boyajian's star, because we wanted to understand what sort of radio interference there was going to be looking in that direction. And this map had just come out, and we're like, oh, well, let's just look and see where the 21 centimeter emission is coming from. And this incredibly powerful tool had just come out, and it was just fantastic.
Yeah, I mean, I'm guessing that the actual... Like, this is just the pretty picture that they add to the cover, in the pre-press, and they release that to the public. But in fact, there's a place you can go and look at any region of the sky and see very detailed information about that region, so that, as you said, you can get rid of this noise as needed.
Right. So all the images and videos that you can see of this map, these are just sort of the pretty version of what the data actually look like. There's actually an incredible volume of data that are all part of a public astronomy database. I think it's hosted in Strasbourg, but you can look everything up online. And I was trying to navigate my way through all the tables, and there's just what petabytes of data. It's incredible.
Yeah. And this is becoming a lot more common in sort of all fields, right? These big surveys, this like the, like the Sloan Digital Sky Survey, and this one in hydrogen, and places that you can go and sort of, instead of necessarily getting the telescope time, you can sort of look at things in bulk, right?
Yeah, you can do that for sure. Though I'm almost positive that we're not done actually mapping all of the 21 centimeter hydrogen in the galaxy. I mean, this map is great, and it's the highest resolution full sky map we have, but you can go to finer resolution. And for some areas of science, you're going to need to do that.
Yeah.
But this will give you sort of a good first idea if you're looking at more local things or smaller scale things. This will give you a good idea if you need to actually make those additional observations. And if you're looking for things far away, I don't know, Paul, you might have a better idea of how fine the detail you need for more extragalactic or cosmological things.
Yeah, you need very high resolution, and you also need very high resolution in frequency. So you can't just make one map at one frequency and then another map at another frequency that's like 100 megahertz away. You need very, very high resolution in frequency. So many, many, many layers of maps, so you can tease out that evolution of the cosmic structure.
Sure.
Fantastic.
Yeah, so we're definitely not done, but this is still a great step forward in mapping hydrogen.
Three-dimensional radio tomography.
But
There you go.
speaking of things that are done, James Webb got its sun shield.
Well, we can't just keep talking about radio astronomy. It's kind of fun.
Without noisy astronomer here, I don't
that was
think
a very awkward segue.
No way. I'm really quite proud of how smooth that segue went, actually.
We're going to agree to disagree, which means you're wrong.
All right.
James Webb finished its last layer of its sun shield. So James Webb Space Telescope is an infrared telescope, which means it has to be cold. If it gets too hot, it won't be able to see infrared radiation. It'll just see the glow of its own body. It won't be able to see anything useful. So step number one for JWST is to put it in Lagrange point number 2, which is on the opposite side of the Earth as the sun is. So the sun kind of blocks the sun, and the sun is super hot, and so that's really handy. But the Earth and the moon itself are emitting infrared radiation, so we need to block that light. So for James Webb Space Telescope, they've finished building 5 tennis court sized shields made of highly reflective material and then separated by vacuum between these layers, so that by the time you actually get to the other side, to get to the actual telescope that's doing the observing, it's really, really, really cold. There are other ways of doing infrared telescopes up in space, like having active cooling mechanisms, but those eventually run out of fuel, and that limits the lifetime. So I believe James Webb is also going to be actively cooled, but it'll have a much longer mission life because of these very large shields. And they're done.
Right on. But, I mean, this is just, another sort of step in this process. We're still not launching James Webb until, and by we I mean they, until October 2018. So there's still lots of work to be done.
Yeah, so they finished the primary mirror, I think, earlier this year. Now the sun shield is done. The spacecraft bus itself, I think, is done. There's a few more instruments that need finishing, and then they got to put it all together, and they got to test it in vacuum. They got to make sure that this stuff, all the components are at a really, really high temperature tolerance. Like these shields have to be really, really, really good at reflecting light, because if they're just a little bit off, and one little piece of that giant primary mirror gets a little bit too warm, it will start to warp and flex and bend, and then that will screw up our image. That will screw up our accuracy. So we have to test all this really rigorously because we kind of only get one shot at it.
But it's, I know that with these infrared telescopes, they're cooled down. This is the way they're cooling it. Is that they're shading it from the sun and letting it get cooled by the background temperature of the universe.
I'm pretty sure. I'm not 100% sure. Maybe Kimberly knows. I think there is also active cooling in the James Webb Space Telescope, but because of these giant sun shields, they don't need to use as much coolant. They can use a smaller amount of coolant, which means the mission can be a lot longer than a traditional space-based infrared telescope.
Yes, I agree with you. There is active cooling, which puts a cap on the lifetime, but they're trying to extend it as much as possible.
All right.
And it looks awesome. So there's that too.
It does.
Yeah, it's super. Have you actually seen a mock-up of it? Like, have you actually stood beside the?
No, and I've only seen pictures of it, and then I always imagine in my head that it's like a traditional like spacecraft, like the size of a bed or a room or something. Yeah. And then I see pictures where there's people walking around and go, "Oh, that's a really big thing."
Yeah, we had there was a model of it at South by Southwest about 4 years ago or so, and I got a chance to see it. Yeah, it's like the size of a tennis court. Like, it's just monstrous, and the mirror itself. I mean, you think of the Hubble Space Telescope's mirror, it's like 2 point something meters, 2.4 meters, I forget what it is. And this one is just like, it's like you take 7 Hubble Space Telescopes and just arrange them in a hexagon. It's just going to be such a phenomenal instrument. The amount of light gathering capability of this thing. I mean, the stuff, when we talk about Hubble doing all these really cool observations of these really distant galaxies, and they're using gravitational lensing, they're doing this complicated bank shot. James Webb is just going to have the raw horsepower to just see this stuff directly. It's just going to be...
It's a big bucket.
Yeah. I mean, we'll get a shot at those first, the very edge of the observable universe, some of the earliest formations. I really hope it makes it to space.
Yeah, that'd be nice.
Yeah.
So James Webb is actually going to complement a lot of these cosmological radio surveys that we're doing, where James Webb is like a pinpoint in trying to image individual galaxies when they first form, while the radio surveys at this epoch are looking at the large-scale distribution of gas. Those are actually going to work in tandem so we can tease out how stars and galaxies form.
Oh, just amazing. Kimberly, let's talk about the first light on the VLT's adaptive optics.
Yeah, so speaking of incredible light gathering power, that's my segue.
Nicely done. Way better than mine.
Segue. Right, so the Very Large Telescope, or VLT, which is out of the European Southern Observatory, has just installed the largest adaptive optics mirror ever created on one of its 8.2 meter telescopes, which is the UT4, I am told, or Yepon? I don't know how to pronounce that. UT4. So the VLT has 4 of these 8.2 meter telescopes, which can either work independently or in concert together. They're incredibly powerful, but as all ground-based observatories are, they are subject to atmospheric distortions. So any light that's coming in from the sky gets bounced around by the atmosphere before it hits your telescope, which can make ground-based observations kind of blurry and fuzzy and inconsistent. And so in order to get around this, we've developed systems called adaptive optics, which correct for real-time distortions due to the atmosphere that impact your image. And now VLT being at the forefront of ground-based observations for, I think, nearly 2 decades, they have all had adaptive optics systems for quite a while, but they use laser adaptive optics instead of the deformable mirrors, each of which has their own pros and cons. But essentially, the laser adaptive optics correct your images after the light has already hit the telescope, and the deformable mirror, which they've just installed, is actually part of the light path of the telescope, so it corrects it on the way. And they're useful in different situations, but this way, the VLT can handle really high-scale adaptive optics in just about every single situation. And I'm told that like this mirror is sort of a technological revolution in terms of adaptive optics because it's over a mirror in over a meter in length. They've placed it at the secondary focus of this telescope, and there's I think nearly 1,200 little what do they call them? They call them actuators.
Right, they're like little pistons, right, that push
like
and deform
1,200 little actuators that can change the shape of this telescope very, very minutely, so they can do very fine scale corrections to all the images, which allows you to get incredible precision, very high resolution, and so you don't get any of those atmospheric distortions. Just pretty awesome.
It's kind of amazing, you know, we're talking about James Webb, but the ground-based observatories are taking leaps and bounds as well.
True.
I mean, the VLT is, you know, the Magellan is going to be the next big telescope that's going to be set up down in that same region. There's the 30-meter telescope that looks like it might be moved to the Canary Islands. We're still sort of getting new reports on that. There's other observatories. So even though we've got these bigger and better space observatories, we've got these better ground-based observatories as well. And these technologies
I mean,
just change
people
the game.
like for a while, there's always been some sort of limit on what you could do from the ground just because the adaptive optics technology hasn't been developed enough to, you know, breach those boundaries. But, you know, with this new adaptive optics mirror that's so incredibly precise, they're going to start pushing ground-based observations. So they're not only matching the best that the space-based can do for now, but starting to push past those. And the systems that they developed for the VLT now and have started testing and putting into place, they're going to be on all of the future ground-based telescopes like the European Extremely Large Telescope.
And the possible overwhelmingly large telescope.
Yes. So the EELT will have similar adaptive optics systems on it, and hopefully they'll share this technology with some of us over here in the States because we'd like it too.
Yeah, and then that revolution, you've got the adaptive optics, you've got the with these, you know, the laser guide star and the actuators that are pushing it, and then you match that with the interferometry where they're actually merging the light from multiple telescopes, and as I said, you know, it's a real revolution. And then finding even better and colder places and higher places to put telescopes. So even if James Webb isn't successful, there's some pretty exciting ground-based observatories in the works. So
I feel like saying something like that should be like saying Macbeth in the theater. That you don't ever joke about James Webb not working.
Oh, maybe I've been doing this job for too long, and I just wrote an article about the Mars curse, and only half of the spacecraft sent to Mars actually, you know, survived. So I guess you're right. I shouldn't jinx it.
Yeah.
Curse.
Hey, speaking from someone whose team just overcame a curse, I know something about it. So don't say it.
That's right. You were wearing some kind of hat last time we saw you,
right? I might have been promoting a certain baseball team who just won the World Series for the first time in 108 years. It was awesome.
Congratulations. You played that game of sports ball really hard.
Yes, I personally played that game of sports ball really well.
Nicely done. All right, Paul Matsutter, let's talk about this dark matter, as you say it.
Yeah,
and,
I know some people only listen to this show. I hope they recognize the air quotes.
Yeah, they couldn't see my air quotes.
The malicious
so allow me here.
That
dark matter. There.
Stop
I put that right
doing
in
that.
Well, right. So last week you were here, you joined us, you talked about how, in fact, dark matter and dark energy do exist, even though reports were put out that were, you know, cast some aspersions on some of the science, but in fact they were
tried to throw some shade on it.
But they were, you know, I blame more my astronomy journalist cohorts at their terrible job of reporting this news than the actual science news that there was. So we take all the blame. And now, why don't we talk about what dark matter?
You can take like 3/4 of the blame. I'd say 1/4 of the blame. There was some shoddy science being published.
Yeah,
but yeah, so we know that dark matter exists because we can infer its gravitational presence, but we have no clue. Well, we have some clue of what it might be. And there's experimental efforts, observational efforts to try to pin down more properties of whatever particle is generating, or what is the dark matter, what that particle is. There's also theoretical efforts of sorting through the standard model of physics and going beyond the standard model of physics to kind of tease out, are there any new particles out there that fit the bill? And if so, what are the properties of those particles? For example, the mass. If dark matter is this very, very lightweight particle that just fills up the universe, there could be a ton of these particles floating around everywhere. They just have a super, super tiny mass. Or there could be still a lot, but slightly fewer of these particles with just a little bit more mass. We have constraints on the mass, both from observations of the growth of structure in our universe, from searches of dark matter that haven't turned anything up yet. But it's always interesting to come at this from a theoretical perspective. And some researchers did just that. There's one particular dark matter candidate called the axion particle, and they ran some supercomputer calculations, actually, looking at this possible range of masses of this particle. And they came up with something of, I lost it in my article here, something like 10 billion times lighter than an electron. So if you have one electron, it's as massive as 10 billion of these axion particles. That means every cubic centimeter of the universe has, on average, 10 million axion dark matter particles streaming through it, which is pretty cool.
But what is it?
If this calculation is correct, then this is predicting a mass and some other useful properties of what the dark matter particle might be. Now it's up to the experimentalists who are already searching for it. If they happen to find the signal of a particle in this mass range with these properties, that means these theoretical physicists got it right, and they probably win a Nobel Prize. And that would mean the dark matter particle is this exotic kind of particle called an axion, which is motivated from our understanding of particle physics.
But does the axion, like the mass of the axion, does that fit within the range that's capable of being generated in one of these larger, like in the, in the LHC? Like, can we generate these axions as predicted?
Yeah, so I think again, a lot of this is very model dependent because we don't understand what the dark matter particle is. So there's a very broad theoretical range of what could it be to explain all the observations. Some of these models, some of these theories are accessible by the Large Hadron Collider. Not directly, but if we look at certain kinds of interactions, there may be certain deficits in mass or cross sections or something that would hint towards the existence of one of these particles. Some models are accessible by direct observation, like the cold dark matter search that we have down in the Homestake mine in the United States, a few other sites around the world that are looking for a stray dark matter particle. There are also dark matter particle candidates and models that are not accessible by current experiment or observation. Those are less interesting because we can't tell if they're right or not. So it's very, very useful to have theorists putting out models, putting out ideas, calculating masses, calculating potential cross sections, because they gives us observational hooks.
And for those of us who maybe don't have the particle physics to the same level as you, where does the axion fit within the sort of the general model of everything?
Yeah, so an axion particle is actually a hypothetical particle that's an extension to the current standard model of particle physics. And we think we need an axion-like particle because we see a certain kind of interaction. I know I'm being super vague here. We see a certain kind of interaction that is supposed to be symmetric, but isn't always symmetric. And in order to explain that, this mechanism was developed to explain that symmetry breaking process, and in that process a new particle like floods the universe, which might or might not exist.
So is this sort of going down the path of supersymmetry then? Is that what you're...
It's not quite supersymmetry. It's like an extension of the standard model of particle physics, but not in the direction of supersymmetry.
Right, but they don't sort of fall in this current categories of bosons, and right, they're outside of the standard matter that we
I
know
think
of.
the axion would be, it must be a fermion.
Right. Like an electron, right?
Like an electron, yes.
Yeah, okay.
Or like a quark or something like that, but just with a very, very, very small mass.
Right.
And so the axion is one dark matter candidate. There are other dark matter candidates that come from supersymmetry theories.
Right. Well, I mean, this is such an interesting way to go about this process, right? Like with a lot of things, when they do these discoveries, they're just like, you know, they make it, they run the experiment and out comes some output and they make their discovery. But in the case of dark matter, it literally is they're cornering this concept into a smaller and smaller box until they can finally get it.
Yes.
You know? It's running out of places to hide.
The different paths we're going. Observations of the cosmic microwave background, observations of the growth of structure in our universe, observations, even things like the number of satellite galaxies around the Milky Way help us understand dark matter. X-ray and gamma ray observations, hunting for dark matter. Direct observations, things that are trying to capture dark matter particles, detectors on Earth, the Large Hadron Collider, like so many different branches of physics looking at all these different ways. And that's a perfect way to put it, is just we're trying to put dark matter in a corner to find some signal. Right now, it's just a matter of, well, it's not this one, it's not there, it's not over here, not quite there yet, that mass isn't right, it has to be smaller, okay, it has to be bigger than that, like.
Yeah, no, and that's, I mean, I always just find that so interesting, you know, when people like just almost, they have this ad hoc, like, I don't like dark matter, I don't like the, you know, it bothers me that there's this, but this, like, it's there, it's a mystery, and we don't know what it is, and you can't kind of rule out its existence, so you just keep knocking away at the various parameters, and I guess whatever is left, no matter how bizarre, has to be true.
The worst case scenario is that in 10 years or 20 years, we have one set of experiments that rules out like a big patch of parameter space, like masses and cross sections of dark matter. And then we have other experiments that come from the other end and rule it out, and there's no space left for a dark matter particle. Then we're in trouble.
Right.
Then we really got to figure something else out, but we're not there yet.
Right. That it could even be like two separate.
There could be multiple species
separate things
of
or
dark
multiple
matter.
things that are causing it.
There could be interactions in the dark sector. I mean, who knows if the dark sector of our universe is just boring and dumb, or as rich and complicated as the baryonic sector, you know, the light interacting sector. We just don't know.
Yeah. And as I sort of mention to people all the time, that you are alive when this is getting figured out. I mean, we see older science, the things that Einstein figured out, the things that Newton figured out, without having to go through that dirty process of people proposing theories and working out the math and proposing ideas and getting shot down, and you know, that whole process of a complete mystery, going from discovery through understanding to finally being able to have a pretty good sense of what it is that's going on. And you happen to live at a time right now when you're watching this play out in front of you. So So don't worry. The science is moving forward, and be fascinated by the process and intrigued by the mystery. And I love all the little pieces and each little step forward. You get to fit that into your understanding of the big picture, and I think this is just great.
Absolutely.
So, fantastic. All right, so we're going to sort of wrap things up here, sort of move to the next show that we do. So I just want to remind everyone, if you're watching this right now and you want more space, we're going to be moving over to Astronomy Cast, which is going to be over on the YouTube channel for Astronomy Cast. So you'll want to, I'm sure someone will put a link somewhere, and you can sort of follow to the next show. And we'll be doing that starting in about half an hour. And that's with Dr. Pamela Gay. I think we're talking about clickbait titles in science. So this is going to fit a little close to home, I think.
That'll be fun.
Yeah. So let's give everyone a chance to find out more. So, Paul, where do we find out more about you?
You can follow me on Twitter and Facebook. I'm Paul Matt Sutter. Or you can visit pmsutter.com, where you'll find links to all my stuff, including this appearance on Weekly Space Hangout right now. There'll be a link, I promise. And you can also check me out on askaspaceman.com. That's my very own podcast. That is very fun.
What was your most recent episode? You had a pretty great title.
I don't know. What was it? Oh, what is the shape of the universe?
Yeah.
And the answer, it's flat, but here's the kicker. You have to listen to the whole episode. There's 18 possible shapes for a flat universe.
Torus, cube, polyhedron, dodecahedron. I'm done.
Saddle shaped.
A rhombic dodecahedron is one of them. And that, it's connected in one dimension, or one dimension with a flip, two dimensions with a flip, three dimensions with various angles of rotations. There's 18 known shapes of connected flat.
Okay, enough. Spoiler alert.
I should have taken cosmology from you, Paul.
It's fun.
Go to watch his channel. Kimberly, where do we find out more?
Well, after that, it's pretty short. People can find out more by following me on Twitter at AstroKimCartier, or by going to my website, KimberlyCartier.org.
Fantastic. And once again, if you're watching this on the YouTubes and you haven't already subscribed, just click subscribe. It's the right thing to do. And that way you'll get this show every week. You'll find out all the Guide to Space videos that we're doing. And if you want to go to that next level and you want to catch the show live, click on the little notification bell so you'll get a live notification. Once again, big thanks to all the folks at the Weekly Space Hangout crew for maintaining the chat, bringing in our guests. Really appreciate all your help. Thanks to everyone who watched. Absolutely fantastic. Next week, do we know who we're going to be talking to next week? Pat Ammons from Space Camp. Ooh, that'd be cool. I always wanted to go to Space Camp. Pamela went from Astronomy Cast. I love in the chat the people are posting what the clickbaity titles to what our episode is not
also, I did not say golden baked.
Yeah.
I said rhombic.
The third minute of today's Astronomy Cast will make you gasp in horror. I promise. All right. Well, thanks everyone for watching.
Reasons to love space.
We'll see you all next week. Oh, right. One thing. Go ahead and post any titles if you can think of any that we can steal for the name of this week's show, and we'll just go ahead and post those in the chat, and we'll borrow one. Apart from that, see you all next week.
See ya.
Where's all of us? I'm gonna say that. We'll do that. There we go. Now we can all say. Now we're Brady Bunch, so we can all say goodbye.
Bye.
Bye.
Bye, Fraser. Thank you.